Okay, today's speaker is Tane Vergili from Karadeniz Technical University or Karadeniz Technical University. She will be talking about persistence modules and the interleaving distance. Okay, please go ahead.
Thank you. Thank you very much for inviting me, and thank you for adjusting the timetable so I can be here. Today, I would like to talk about persistence modules and the interleaving distance. And I would like to start with this drawing. So when you ask the pioneering researchers in this area what the aim of topological data analysis is, they always sketch the first diagram. So you are going to start with the data, and then you are going to compute, or you are going to get the increasing family of complexes or topological spaces. And then if you apply homology functor with coefficients in some fixed field, then you get persistence module. And now you have a collection of vector spaces and linear maps between them. So you can also compute the summary in a barcode representation, persistence diagram representation, or persistence landscape. So this is the workflow of topological data analysis. So if you start with, so let me give a motivation. So if you start with a data, so let's assume that X is a finite set in Euclidean space, and let's assume that these points are representing a geometric picture. And you would like to understand the shape of this data. Then you might apply topology. One attempt could be considering the topology of subspace topology of this collection. But in that case, this is a finite set, and X is a subset of Euclidean space. So the subspace topology will be discrete, and it won't tell you an interesting story. But the nicest attempt could be constructing simplicial complexes on these points. So the procedure is, let's say, check complex procedure. So you are starting fattening these points by epsilon balls. And this is the idea. If two balls intersect, you are going to join two vertices or two vertices by a line segment. But if three balls intersect at the same time, you are going to join these three vertices with filled triangles. So if you generalize this idea and keep this process, you get a simplicial complex. But in the second picture, we see that when epsilon is too small, then the balls won't intersect. So the corresponding simplicial complex will contain simplices, but they are just zero simplices. But when epsilon is too large, then all balls will intersect, and the corresponding simplicial complex won't tell you interesting things, because this has a zeroth homology. So the question is, what is the best epsilon to understand the shape of the data? But the answer is there is no best epsilon. In fact, we are focusing on the evolution of the process. So when epsilon increases, we have a collection of simplicial complexes. And as you can guess, these are nested sequence of simplicial complexes. And then when you apply homology functor with field coefficient, now you have vector spaces and linear maps between them. So this is the idea of TDA. And then you can also consider the lifespan of each generator and then record in a barcode representation or record on a persistence diagram. So this is the story of topological data analysis. So let me pass to algebraic structures. So now I have vector spaces and linear maps between them. So let me generalize this idea and let me talk about the persistence modules. So let me fix my notation. Let's say K is a field, and then let's consider a poset. So this poset could be, in practice, that could be R with the usual order, or the set of integers with the usual order, or the set of natural numbers with the usual order, or the poset could be a finite set. So let's say in brackets n, where n consists of n elements, n minus 1. So just think about a poset, then a persistence module is a collection of vector spaces and linear maps between them. But there are two conditions to say that the collection is a persistence module. The first one is the linear map from a vector space to itself is the identity map. And if A is less than or equal to B and B is less than or equal to C, then the map from A to C is nothing but the composition of these two maps. So imagine that the poset is the set of real numbers R. So just represent a persistence module as a real line. So in this case, you are assigning to each real line, you are assigning each real line to a vector space, let's say M of A. And between M of A and M of B, there is a linear map. Let me label it by V sub A to B. And then the linear maps should respect the composition. So the composition of two maps is equal to the linear map from M of A to M of C. You may think about a persistence module as a real line R, and at each point you are considering vector spaces and there are linear maps between them. But the direction of each linear map should be to the right. So maybe if you are familiar with the categorical theory, you can also define a persistence module in terms of a functor, in terms of a topological point of view. So let's say, so this is a poset. So we can consider a poset as a poset category. And then a persistence module is a functor from this poset category to the category of vector spaces. Then you are assigning to each object a vector space M of A. And what about the morphisms when A is less than or equal to B? Then that means you are assigning to this morphism a morphism from M of A to M of B. So this is a functor from the poset category to the category of vector spaces. So in general, when we say M is a persistence module, we always consider M from the poset category R to vect. Because any poset can be considered as a poset on R. So you can see the diagram. So from now on, unless stated otherwise, when we say M is a persistence module, we can consider that it's a functor from the poset category R to the category of vector spaces. So let me give some examples. For instance, the first one is the zero module. So zero module is a persistence module. So again, you are considering a real line, and at each spot, you are assigning zero vector spaces. So the linear maps, of course, between them are zero maps. So this is the zero persistence module. Or we can talk about ephemeral persistence module. So this time, this is a persistence module. At each spot, you have vector spaces, but the linear maps are all zero maps. So that means the lifespan of each generator. So each generator borns at the same time and dies at the same time. So their lifespan is short. So this is ephemeral persistence module. Or we can also define Q-tame persistence module. So Q-tame persistence module is a persistence module where each linear map has a finite rank. So the M of A or M of B are not necessarily finite dimensional vector spaces, but the linear maps have a finite rank. So let me give another example. So let's consider an interval 1 infinity in R. So this is an interval. And again, you can look at the illustration. You are assigning each element in this interval the vector space K, the field K. And if you are outside of this interval, you are assigning each point the zero vector spaces. So what about the linear maps? So the linear map, if you are inside of this interval, the linear map is the identity map. But if one vector space is here, but the other is here, or if two vector spaces are outside of this interval, then the linear maps are the zero maps. And you can generalize this idea to any interval. So let's say J be an interval in R. And if you are inside of this interval, you are assigning to each point in that interval the field K. And if you are outside of this interval, you are assigning 0 vector spaces. So this is what we call interval module. So now let's say we have two morphisms. So we have two persistence modules. And let me define a morphism between persistence modules. Again, we have two persistence modules, let's say M and N. Or we can also consider a persistence module on a real line. So in this case, a morphism between M and N is a natural transformation phi. So here I have, so phi is a collection of linear maps. So at each point I have, at each spot I have vertical arrows. So let me say P sub A. So this is a collection of linear maps going down such that each rectangular diagram commutes. So this is the definition of morphism between two persistence modules. A collection of linear maps, or in a categorical point of view, it's a natural transformation from M to N. And if each phi sub A, so if each linear maps are isomorphism, then we say that these two persistence modules are isomorphic to each other. So what about the direct sum? So if we have two persistence modules, then we can also talk about the direct sum of two persistence modules. Again, it's a functor from R to vect. But this time, the objects are the direct sum of two vector spaces, M of A and N of A, and the linear maps are, so let me show here. So the linear maps are the direct sum of these two maps. So you can also consider the direct sum of two persistence modules, and you can extend this idea and you can define the direct sum of a collection of persistence modules indexed by an arbitrary set. So you can also consider alpha in A M alpha. So you can also consider the direct sum on an arbitrary set. So a persistence module is said to be indecomposable if M is isomorphic to direct sum of two persistence modules, then this implies either N or N prime is a zero persistence module. In that case, we say M is indecomposable. And here is the theorem: interval modules are indecomposable. So if you consider any interval module, so everything is the field K if you are inside of this interval, and the outside everything is zero. So if you consider this interval module, this is indecomposable. This is coming from the fact that the endomorphism ring from an interval module to itself is isomorphic to the field K, and the idempotents in the field K are 0 and 1. So there is no non-trivial idempotent element in K. So this is coming from this reason. So if you start with the assumption that an interval module is decomposable, then you will get a contradiction with this fact, because of this fact. So because the endomorphism ring from I to itself is isomorphic to K. And we say a persistence module is interval decomposable if a persistence module is isomorphic to direct sum of interval modules. So here, each I sub I R is an interval, and here you can consider the arbitrary set if you consider the direct sum of these intervals. So if we say this is interval decomposable, and this representation is unique up to the reordering. I mean, if you have two representations, So let's say M is isomorphic to the direct sum of these interval modules, and M is also isomorphic to the direct sum of these interval modules, then M is equal to N, and the sequences, I mean, the intervals are the same up to reordering. So the representation is unique.
Tane, can I ask you a question?
Yes, please.
So when you say interval, do you mean that there's a closed interval or half open intervals are okay?
Any interval is welcome. So you can consider an interval.
Then why can't you write 0-2 interval as direct sum of 0-1 interval open and 1-2 interval closed? Like, why can't you direct sum by taking one part open, other part closed?
Yeah, we can also consider any interval modules. For instance, 1 infinity or 0-1 or -1 and 2. We can consider any interval here. So in this case, M is interval decomposable.
But wouldn't you be able to direct sum 0-1 open interval module with 1-2 open? One side is closed so that you have the full interval? Is it?
Yeah, if you think about the first one, so if you think about this one, so everything is 0 outside of this interval, and everything is K inside of this interval. So this is the interval module.
Okay.
So everything is K, and the rest is 0.
So if you direct sum this with close at 1 to say open to 2 interval,
And this one?
Yeah.
And this one? Okay, so this
Don't
is...
you get the 0-2 interval? Is it too naive to think that way?
No, this is the direct sum is... Okay, so...
So intervals are not indecomposable. Is it?
So when you consider this, so let's say this is N. And in this case, N of 1 is K. So at the spot 1, N of 1 is equal to K. And
is this the same as the 0-2 interval with 0 open and 2 open?
no, it's not.
Why not?
I mean, it will be isomorphic to 0-1, 0-2 in this case, because when you consider the direct sum of this is 1 and 2. So you're saying this 0 and 1, right?
Yeah.
And if you consider the direct sum of these two interval modules, so it will be isomorphic to 0 and 2. It will be isomorphic to an interval.
So interval modules are not indecomposable.
Yes.
Okay. Maybe I misunderstood. They are not indecomposable.
Yes, they are indecomposable.
Yeah, but we just decomposed it, 0-2 interval, into 2 summands. That's why I'm confused.
Yeah, I am also confused with your question.
Maybe
this is other decomposition.
Yeah, but
no, but you can't decompose it because the maps doesn't fit, right? On the right hand side, you have identities inside 0-2. On the left hand side, at the breaking point 1, you have 0 maps appearing, so that doesn't make doesn't give you a commutative diagram.
Maps.
Yes.
Okay.
Thank you.
Thank you. Thank you.
And here we have this structure theorem. So if you consider a persistence module on this poset category, and if this poset is finite, or if each vector space M of A is finite dimensional, in that case, this persistence module is isomorphic to a direct sum of interval modules. So whenever P is finite or each vector space is finite dimensional, this is isomorphic to interval modules. So this is coming from this fact. So if you consider a persistence module over a finite poset, let's say M of 0, M of 1, M of N, and let's consider the sum of all vector spaces. So this is a finitely generated module. And when K is a field, the polynomial ring is a PID, is a principal ideal domain. And A is a module over the polynomial ring by this given action, by this action. So a finitely generated module over a PID has a structure, there's a structure theorem. So A is isomorphic to the free part and the torsion part. And free parts, each element in the free part corresponds with the interval B sub I infinity. And each part in the torsion part represents or corresponds to the interval Rj and Rj plus Sj. So this interval represents a generator which borns at the time Bi and never dies. But this interval represents a lifetime of a generator, so which borns at the time R sub j and dies at the point R sub j plus S sub j. So if a persistence module is defined on a finite poset, or if each vector space is finite dimensional, then M is isomorphic to a direct sum of interval modules. So for instance, if you consider this compact manifold and if you consider this height function, then one can consider the sublevel sets. So F sub A, so this is X in X such that F of X is less than or equal to A. So you can consider the sublevel sets. So this is a compact manifold and there are finitely many critical numbers. So when you consider the sublevel set filtration, so when you consider F sub A, you will see only one point. But when you go up and when you consider the sublevel set for at the point B, now you have two connected. So you have two connected components. And these two components are going to merge when you come to the level C. So if you keep this process, then you have 6 critical numbers and you can consider the sublevel set filtration. And if you apply the homology functor, the 0th homology functor or the first homology functor, so you get vector spaces and linear maps between them. And all information is contained in this in the sequence of in the collection of linear maps and vector spaces. So here, if you consider the persistence modules of X, so that means there is a one generator born at the point A, at the level A, but this point never dies. So it persists forever. So you are going to write, so one generator born at the level A and never dies. But at the level B, one component is born, but this component died at the level C. So you are writing a one generator was born at the point at the time B and die at the time C. And you can keep this process. So all information is contained in a persistence modules, and you can also represent these points on a diagram. For instance, for the 0th homology, so A infinity is here. So you are considering the extended plane. So you are allowing that the second coordinate could be also infinite. So A infinity is this point, and then you have a generator, so you can try to plot its lifetime, its lifespan. So BC is here and DE should be here. So if you are close to the diagonal, so that means your lifespan is short. But if you are away from the diagonal, so that means you persist more. And this is for the first homology. So you know this is homeomorphic to a circle, and at the level F there is a one-dimensional hole, and this hole borns at the point F, but it never dies. So there is a point here, F infinity, which represents for the first persistence homology.
Tane, can I ask a question about?
Yes, please.
Just last slide. When you write H0, this intervals, direct sum of intervals, you make some choices, right? The component for the A survives, it continues to infinite. You say the component that starts with B dies. You could have thought the other way, that A dies and then the one with B continues. Do you get some way isomorphic modules, or do you always have to pick the first one?
The older one, I mean the oldest one, always lives forever. So this is our ancestor, and he lives forever. So
okay.
When these two merges at the level C, so we always consider that the first one always wins. Okay. So it persists forever, but the second component died at the level C.
Okay. Thanks.
Thank you. And let me go back to algebraic structure. Again, I have two persistence modules, and now I'm going to consider two morphisms from M to N and from N to M. But this time I have two morphisms, let's say phi and psi. But now I am allowed to shift the maps by epsilon units. So let's say if I have two morphisms which satisfy the following four diagrams, then I say that these two persistence modules are epsilon interleaved. So the first one is when you are at this point M of A, so this is a vector space, and you shift the map by epsilon unit. Now you are at the other persistence module at the level, at the spot A plus epsilon. And also there is an internal map on the persistence module. Now you are here and you shift the map by epsilon, and now you are in the persistence module M. And there is an internal morphism, linear map between these two vector spaces. And if this diagram commutes, so we expect that this diagram commutes. And on the other hand, we have another morphism from N to M. So we start from here and we shift the map by epsilon. And for the same, with the same procedure, this is N of B, and we are going to shift the map by epsilon. And these are the internal linear maps. And we expect that this diagram commutes. And another diagram, so we are here, M of A, the vector space, we go down and shift the map by epsilon. So we are at this point A plus epsilon, then we go up by the map psi, and now we are at the point M A plus 2 epsilon. And we expect again that this diagram commutes. And similarly, if you are in the persistence module N, you can go up and then you can go down with these two maps, and you expect that this diagram commutes. So if you can find these, the collections of phi and psi, then you say that M and N are epsilon interleaved. And of course, one trivial observation is that if M and N are isomorphic, then M and N are zero interleaved. Because if they are isomorphic, you know, there is a map, there's a vertical map, and this map has an inverse. So you can also talk about the maps to go up and the maps to go down. So if two persistence modules are isomorphic, we can say that they are zero interleaved. So this is the interleaving distance, but interleaving distance measures how far two persistence modules are from being isomorphic. So you consider all epsilon interleavings, and then you are going to consider the infimum of all epsilon such that M and N are epsilon interleaved. So this is the interleaving distance. You consider all the epsilon interleavings, and then you consider their infimum. And if you cannot find such epsilon, then you are going to set that the interleaving distance between two persistence modules is infinity. So here are some facts, and here is the problem. So the interleaving distance is, so this should be equal, sorry about this. So the interleaving distance is symmetric, and it satisfies the triangle inequality. But if two persistence modules are isomorphic, then we know that the interleaving distance is zero. So the infimum is again equal to zero. So if two persistence modules are isomorphic, then the interleaving distance is equal to 0, but the converse may not true in general. Maybe I can give a simple example. For instance, just consider a 0 persistence module. Everything is 0. And think about a persistence module. Up to the point 0, everything is 0. But at the spot 0, let's say I assigned a field K. And again, the rest is 0. And you will see that this is, so if I say M and N, so I observe that the interleaving distance is 0, but they are not isomorphic. So if you consider any shifting map by epsilon, you will see that these two persistence modules are epsilon interleaved for every epsilon. So you have 4 commutative diagrams, but these two persistence modules are not isomorphic. And also there is one problem. So the interleaving distance may take infinite values, because I say that if no such epsilon exists, the interleaving distance is infinite. And again, here there is another problem. When you consider the collection of all persistence modules, then you can say that it is not a set. So when you would like to say a metric space, or when you would like to start the definition of a metric space, you start with let X be a set. But the collection of persistence modules is not a set. So this is the first problem. And the second problem is the interleaving distance does not satisfy all the requirements to be a metric space. So this part is not true here. And also there are some values, and this is possible that the interleaving distance is infinite. So if the converse is not true, we say that this is a pseudometric. So this is a pseudometric. Maybe we can talk about pseudometric instead of metric space. But one problem is the collection of persistence modules is not a set. So this is the big problem. In literature, there are some papers. They work the interleaving distance on a class of persistence modules. They say lower space. This is also possible, but that study has aimed to consider the topological properties of persistence modules induced by an interleaving metric. So this last one is the biggest problem for this study. Maybe we can also achieve, or maybe we can also get rid of infinity part. But anyway, if we consider the definition of an extended pseudometric, so we are going to start with a set X, and then this metric can also take infinite values. That's why we say extended. And pseudo, the word pseudo, is coming from the fact that when the distance between 2 points is 0, we cannot say that these 2 points are equal to each other. So this is the definition of extended pseudometric, and the interleaving distance satisfies the all requirements to be an extended pseudometric if we can find some sets which is a proper subset of persistence, the class of persistence modules. So if this is a pseudometric, then the open balls will generate a topological space. But at this point, when we consider a class of persistence modules, so this is the class of persistence modules. This is not a set. Maybe we can consider some various classes. Maybe we can classify them, and then we can determine which ones are sets and which are not sets. So this is the class of Q-Tane persistence modules. So all linear maps has a finite rank. The class of Q-Tane persistence modules. So this is the class of ephemeral persistence modules. The linear maps are 0. This is the set of 0 persistence modules. So there is only one element, and that in that persistence module, everything is 0. This is the 0 persistence module. So here, so these are abbreviations: finitely finite interval decomposable. So it is saying that you should work on a finite direct sum, and your each interval should be contained in the compact interval C and D. Finitely finite interval decomposable. So it says, again, this is finite. Sorry. Maybe Siri has an answer. Sorry. Composition is finite and each interval is also finite. I mean, has a finite length. So here FID, finitely interval decomposable. So you have finite sum, but here the intervals could be anything. It has an infinite length. So this is pointwise finite dimensional persistence module. So that means at each spot, each vector space has a finite dimension. Each vector space is finite dimensional. And this is the class of interval decomposable persistence modules. So here, any persistence modules is isomorphic to a direct sum of interval modules. This is a countably interval decomposable. So the index set is countable. And you can consider any interval. So this is countably finite interval decomposable. Again, the index set is countable, but each interval is finite, has a finite length. So you can classify some kind of examples, and then you can consider or you can determine which of them are sets. So this is the Hasse diagram, and each arrows represent an inclusion map. So that means CID is contained in ID. Maybe you may ask, so why the class of pointwise finite dimensional PFD, why PFD is not contained in CID? We should also find some counterexamples. Maybe we can play with modules and we can find some examples. So here is the idea. For instance, so this one is an ephemeral persistence module. So at each spot you have K, but this is not a pointwise finite dimensional, because at the point 0, the vector space has a finite infinite dimension. So this is not a pointwise finite dimensional persistence module. So that means there is no arrow from ephemeral persistence module to PFD. Or maybe that you can consider this interval module. So here, this is countably finite interval decomposable. I mean, the index set, you have a countable set, you have a countable index set, and also this is 0, 1. So each interval has a finite length, but this is not Q-tame because 0, 1 repeats from K is equal to 1 to infinity. So it repeats infinitely many times, and this is not a Q-tame function. It's not a Q-tame persistence module. So you can play with these examples and you can show that, for instance, there is no arrow from FFID to CID.
So Tane, we fixed our poset, I guess, some point to real line.
Real line, yes.
So we're only talking about poset being real line.
Real line,
And in that case, which one of these are sets? So is it still under study or is it known?
No, we determined which of them are sets.
Okay.
So here is the idea. So these are just notation. Of course, this is not the closure of R. I mean, this is not a notation in topology. So R bar is the union of R with the plus or minus infinity. And let's say N bar is the natural numbers and the union of the infinity. And now I'm going to consider a function from the set of all intervals to R. For instance, so this one, let's say this is the set of all intervals in R. And here I have a function from R to 1, 2, 3, 4. So if the interval, so I'm going to consider an interval, let's say 1 infinity. So this is an element here. And I'm going to map this interval under this formula. So if the infimum is contained in this interval, but the supremum is not contained in this interval. So I am here. So I'm going to assign 2. So this is 2. Or let me take another example. Let's say 1 and 2. So infimum is not an element and is not contained in this interval, and supremum is not contained in this interval. So I'm going to consider 1. So the map. So this is going to be mapped to 1. So this is my function, and I'm going to use this function to consider which of them are sets. And in fact, these are the sets, and the rest is not a set. So for instance, so let me give an example. So the class of countably interval decomposable. So let me write again. So you are allowing a countable sum, and each interval can be anything. So this is interval can be anything. So in this case, I'm going to find a map from the class of countable interval decomposable persistence modules to a set of some set. So this is the idea. When I consider any interval here, I sub alpha, I'm going to consider the union. So the first one is the infimum and supremum. So if you consider, let's say, 0 infinity. So the infimum is equal to 0, and the supremum is equal to infinity. I am allowed to write infinity because I am working on here. And what about f of alpha? So infimum, for instance, infimum is not contained here, and supremum is not contained here. And let's say this is equal to 1. And m of I is the multiplicity. Sometimes 2 generators or more than 1 generators born at the same time and die at the same time. So you may also encounter an interval many times in the decomposition. So this represents the multiplicity of an interval. So if you see only once, if you see this interval once, then the multiplicity is 1. And in this case, this is an element in the power set. So there is an injection from this class to a power set. So we can say that this is a set. And if CID is a set, so if I look at this graph, so if the biggest one is a set, then the proper subclasses are also sets. Maybe we can also see what happens when we consider pointwise finite dimensional persistence modules. The idea is the same. So if a persistence module is a pointwise finite dimensional, so that means at each spot, the vector space is finite dimensional. So that means you cannot see the interval I at infinity time. So the multiplicity of that interval cannot be infinite. So in this case, you can also use, so this should be PID, sorry. So you can also use the same function so that the class of pointwise finite dimensional persistence modules is a subset of this power set, because this is an injection. So we can say that this is a set. So for instance, maybe you can ask why the class of ephemeral persistence module is not a set. So at this point, yes, please. No, please.
Another naive question. The set of vector space is not a set, right? All the vector space form a class.
The set of vector spaces?
There's no set of vector space, right? It's also a class, all the vectors spaces. So there you do a trick to make it a set. Do you do the same trick here? Because all the vector spaces will be inside in all of these by constant factors, with constant things. All the vector spaces will be in here. So there they choose representatives in isomorphism class, I guess. Is that like that, or?
So every vector space can construct a persistence module. So in this case, the class of persistence modules is not a set, because every vector space can construct a persistence module. But for the ephemeral persistence case, I mean, if I understood your question, so for instance, for the ephemeral persistence modules, so you can also find an ephemeral persistence modules to each vector space. For instance, you get everything 0, and at the point 0, you get your vector space V, and the rest is again 0. So this is an ephemeral persistence module. And so all vector spaces are embedded to ephemeral persistence module. So definitely you can say, but we use another proof. So we consider cardinal numbers. For any cardinal, we can construct an ephemeral persistence modules. And if two cardinals are not isomorphic, then their corresponding persistence modules are not isomorphic. And you know, the class of cardinal numbers is a class, is not a set. But your idea is, I guess, is better than ours, because it's really nice and simple.
I'm also confused. Just the same question that I've asked, because in the previous slide, for example, maybe it's easier to talk on that. So this decomposition on the left for an element of this PFT, well, any module which is PFT, you're choosing an isomorphism to say that it is of this form, in this direct sum form, right?
Yes, yes.
So I think, doesn't that mean you're looking at isomorphism classes of PFTs?
Exactly, exactly.
Isomorphism class of PFTs is a set.
Exactly. When I say pointwise finite dimensional persistence modules, I mean it's isomorphism. I mean, I consider M, if it's a pointwise finite dimensional, then I consider M is isomorphic to the direct sum of interval modules. Then I am looking at isomorphism classes.
Okay. So that makes sense. Then, I mean, in that case, if you consider all vector spaces, the isomorphism class would be just natural numbers, right? And that's a set, but you have this vector space, it's a class. So in this other example,
yeah, it won't be a non-example anymore, because now if you're only looking at isomorphism classes, this will be just a set then.
Yeah, okay. So I was confused with the isomorphism classes, or I've been looking at the things on the notes.
You need that cardinal example, I think. But you always do isomorphism classes like in the vector space case. Okay.
Yes. Okay. So sorry, I didn't say it, but yes, you're definitely right. I'm sorry.
Just understand.
And if you look at this graph, so you see that the ephemeral is on the ground. So if the class of ephemeral persistence module is not a set, then we can conclude that the class of interval decomposable persistence module, the class of persistence modules, and the class of Q-tame persistence modules are not sets as well. Okay, so at this point, maybe we can say something about ephemeral persistence modules, but because this is a nice class, I mean, so this is not a set, but if we consider a set, a proper set of the class of ephemeral persistence modules, and if we impose the interleaving distance to that set, then its topology will be the indiscrete topology. So this is because if you consider any ephemeral persistence module M, so the ephemeral persistence module, the distance between the ephemeral persistence module and the zero module is going to be 0. And by the triangle inequality, the distance between any ephemeral persistence modules will be 0 as well. So that means when you consider the epsilon ball centered at the persistence module M, so this ball will contain all elements. So this ball will be, so this is subclass. So this ball will contain all sets. So we can say that the topology is the indiscrete topology. So the class of ephemeral persistence module is not a set, but we can consider some subsets maybe, but in that case, nothing is interesting because we get the indiscrete topology. And at this point, maybe we can ask, so so we know the sets, And we can impose the interleaving distance. So this is a pseudometric. And we know that open balls generate a topology. And what about the topological structures of these sets? So unfortunately, none of them is a Kolmogorov space, but all is first countable because an extended pseudometric is a first countable. None of them is locally compact. The first two is path connected, but the rest is not path connected. So the first two are path connected since they are also contractible, and the first three are separable. Maybe I can explain a couple of things about path connectedness. For instance, we may ask, so why FID is not path connected? So maybe I can say something about this. And then these two are still open question. And we can also look at the completeness. So which of the sets are complete? So we conclude that the last two are complete spaces, and all spaces here are paracompact. And for the complete spaces, we can also talk about Bayer spaces. And the last two are Bayer spaces as well. So we can play with the topological structures by using the interleaving distance, and we can ask, so what this set has a topological property. Maybe for the path connectors, I can say something. For instance, we may ask, so why FID, CID, or PFD are not path connected? So for instance, so this is a general theorem. So this is a general lemma. If we have an extended pseudometric space, and in this space, if we have two elements such that the distance is equal to infinite, so they have infinite distance, so we can conclude that there exists no path from A to B. So that kind of spaces cannot be path connected. So this is because of the fact that, so assume not, so let's say there is a path from A to B in S, gamma 0 is A and gamma 1 is B. So let's say that there exists a path. So in this case, this is a continuous function, so it's a path. So we can say that the image of gamma is compact. So if this is compact, then if we can consider an open cover, so the open balls with radius 1, X is in the image of gamma. So this is an open cover. So if this is compact, then we can say that this cover has a finite subcover. But in this case, by the triangle inequality, we conclude that the distance between A and B should be finite, because we have finitely many number of open balls which cover the space. And this is the contradiction, because we assume that the distance between 2 points is infinite. So
But
for the...
in a pseudometric, points which are different may have the same zero distance between them, right? So why this... in a pseudometric, can we think about all these things in the same way? Because you can have different points with zero distance. Maybe some of the infinite part between A and B, some of them have zero distance in the interval A to B. Like, doesn't it affect the fact that it's not a metric space?
No, if you consider this open ball B1X, so the center is X, and you consider the the balls with radius 1. So this cover, so the collection covers the image of gamma, because it's a compact set, and it has a finite subcover. So when you consider the triangle inequality, so you get, the distance from A to B is less than A x1 x1 t, and you can keep this process, and you get that the distance should be finite because you have finitely many open balls. So this won't affect even when we work on a pseudometric space, because the open balls also generate the topology in a pseudometric space.
But you're using image of a compact under continuous map is compact.
Yes.
Does that still work in the pseudometric under? Because things can have zero distance when they're not equal. Doesn't.
Yeah. So any properties which are valid for metric spaces are also valid for pseudometric spaces. For instance, in a metric space, separability, second countability is equivalent to separability or Lindelof spaces. And this is also true for pseudometric spaces.
Okay. Thanks.
I hope this won't affect, this is already, our paper has been published and I hope this won't affect. So maybe for the first three of them, so the spaces of persistence modules FID, CID, or PFD are not path connected. So I can find two elements. So the first persistence module is the zero persistence module, of course, so everything is zero. And the second one, I can have the interval module, zero infinity. So these two persistence modules are contained in FID, in all of them, in FID, in CID, or PFD. And the interleaving distance between M and N is infinite. So by the previous lemma, I can say that there exists no path from zero to the persistence module N. So I can say that these spaces are not path connected. For this one, CFID, we consider M is equal to 0. And again, N is equal to, so let me cheat. So K starts from 1 to infinity, and this is 0K. So these two elements are both in the set of countably finite interval decomposable, but the interleaving distance is infinite. So we can say that these spaces is not path connected. One last thing that I would like to talk about, completeness. So this process is nice for the first four of them. The pointwise finite dimensional, finite interval decomposable, or FFID or FFID-CD. So they are not complete. So one can find a Cauchy sequence. So let's assume that the sequence, the terms of the sequence. So this is the general term. Can find the term. So this Mn. So to this element is contained in all of them. And when you consider this one, so this sequence converges to this decomposition, so interval decomposable persistence module. And this is not a pointwise finite dimensional because at the point 0, the vector space has an infinite dimension. But we should also be careful. So this one approaches, converges to this guy, and this is not an element in PFD, but we know that in a metric space, the limit is a unique, right? So when Mn converges to a point, so that point should be unique, but in a pseudometric space, the limit, if this sequence converges to a point, so it shouldn't be unique. It's possible that M is not unique. And you should also show that there is no element in PFD such that the interleaving distance between M and N is 0. So so we prove that. So this sequence is a Cauchy sequence, but it converges to a point which is not in pointwise finite dimensional set. And PFD contains all of them, so we can say that so these sets or these spaces are not complete. For the other one, maybe what about the complete, what about the proof to show that these spaces are complete? So you start with a Cauchy sequence and find a subsequence such that the consecutive, let's say m sub k and m sub k plus 1 are 1 over 2 to the k interleaved. So find a subsequence such that the two consecutive persistence modules satisfies this inequality. And this is, then we can conclude that when the interleaving distance between two is less than 1 over 2 to the k, then we can say that these two persistence modules are 1 over 2 to the k interleaved, because the interleaving distance is less than 1 over 2 to the k. Maybe we can illustrate this fact. So let's start with a subsequence. So I have a subsequence m sub 0, m sub 1, m sub 2, and I know that each two, so these two consecutive persistence modules are 1 over 2 to the 0 interleaved. So there is a shift map from a minus 1. So I'm doing this pointwise. So for points for the spot A, so what is the persistence module and how can I define m of A? And I'm doing this pointwise. So let me start from a minus 1. So the first two is 1 over 2 interleaved. So there is a shift map from a minus 1 to a minus 1 over 2. And m sub 1 and m sub 2 are, again, 1 over 4 interleaved. So there is a shifting map. So I have a minus 1 over 2. And I map this point to a minus 1 over 4. So if I follow the procedure, and if I consider the co-limits of the maps, I have an element here. So let me say a of A. Similarly, I have another shift map which goes up. So here, these two consecutive persistence modules are interleaved, are 1 over 2 interleaved. So there is a shifting map, takes a vector. I mean, the starting point is a plus 1 over 2, and it maps to a plus 1. And you can also consider these kind of shift maps, and you can consider the inverse limit, the direct limits of these maps, and you will get a B of A. And in this case, if you consider the universal properties of the co-limit and limit, so here I have a map from A of A and B of A. And if I consider the image of this map, so that point, so M of A is the persistence module. So I'm looking for the persistence module M such that the subsequence converges to this persistence module. And I define this persistence module pointwise, and at the spot A, I'm going to assign a vector space image of theta A. So with this construction, I can say I can find a persistence module, and I can say that the Cauchy sequence, Cauchy sequence converges to a point, converges to another persistence module in the given set. So that's all what I would like to talk about today. Thank you very much for your patience. And if you have any questions, I would be happy to answer.
Okay, yeah, thank you very much. Any questions for Tane?
So a few questions I have actually, but so starting with the data, you have these persistent modules you get, and I guess for this work, we focus on the poset being the real line. And so these modules, you don't know which category they come from, all these CFRs, and you don't know, or do you generally have a feeling that it will be in one of those? Then in that category, you have a topology, as I understand, right? So these categories, which one is more possible? These different way your modules will show up, the CRP, PR, I can't tell all of them, but PRF, these categories, which one shows up more? Like that, then you look at its topology, and then why you compare this different topology, the topologies of these different categories. So like, I try to understand it in terms of data analysis.
Okay, so let me find. Okay, so
So these, I say category, but I mean the collections. The ones you establish, they're being sets. So your module is in some of these CID, FID, or FFID. Which ones is more possible that like your data comes up is FFID all the time? Like, do you know?
I mean, your data is a finite set, right? So that means everything happens in a restricted time. So in this case, the most common is FFID-CD because the intervals, I mean, the generator is born at some certain time and die at some certain time. So the bottom one, I mean, the one FFID-CD is the most common that data analysis work on here. But I guess
helps you
maybe
to study
this
on a
one.
bigger set because of the general properties of modules over this.
So this is our motivation. So when we consider topological data analysis, I mean, if a persistence module, so let me go back to structure theorem. So here, so when the poset category is finite or M of A is finite dimensional, so which is okay. I mean, if you work with a data, then each vector space is finite dimensional. So it's isomorphic to direct sum of interval modules. So that means it has a nice representation. So you can represent what's going on here in a persistence diagram or in a barcode representation. But this is the case for one parameter persistence modules. And we know that here we have a persistence diagram for this map. So we call it by the diagram of F. And if we have another function and if we have another diagram, let's say diagram of G, then we can also compute the measure, I mean, compute the distance between these two diagrams. We are going to measure the optimal transport for the cost of the transportation plan because we have a bunch of points here and we are going to consider the distance between them. And we call it the bottleneck distance. And in most cases, the bottleneck distance and the interleaving distance are equal to each other. I mean, the bottleneck distance of two persistence diagrams is equal to the interleaving distance of their corresponding persistence modules. So in practice, we use the bottleneck distance, but this is true for one parameter case. When we consider multi-parameter persistence modules, we cannot represent the data in a barcode or in a persistence diagram, but we can still talk about the interleaving distance. So this is our motivation. I mean, for the multi-parameter case, we cannot talk about the bottleneck distance, but we can still talk about the interleaving distance. And there is an open question in that paper. Can we extend these results to multi-parameter case? But there is a problem because we don't have a structure theorem. So we cannot consider a PID and the structure, but the torsion part and the free part. And we cannot say a persistence module is isomorphic to a direct sum of interval modules. There was another problem for the multi-parameter case, but that was our motivation, to be honest. I mean, in practice, we never use the interleaving distance. To be honest, if you give me two intervals and if you ask me the interleaving distance, if you give me two interval modules, and if you ask me the interleaving distance of two, I always apply the bottleneck distance, to be honest. But this is our motivation. I mean, if you work on FFID-CD, you don't need to consider the interleaving distance. And also if you are working in Q-Tame, and also this is not a class, but this is not a set, but if you work in the class of Q-Tame persistence modules, you can still use the bottleneck distance. This is because the bottleneck distance is still equal to the interleaving distance. Is that your question?
No, I just try to see why study all these different collections. Like, stick with one of them. Maybe study is topology more, but I will intuitively. But studying different collections, what you gain out of it, like basically, like the countable ones, what do they give you? Is it something you use at the end on the classification of modules that you want, or a lot of collections here, right? Different collections. Do they help at the end to understand the collection that you want?
Yeah, if FFIDCD was a complete space, maybe we could use it, because I
you
mean,
put it inside the bigger ones.
exactly,
So
but this is not a complete space.
That's a good. Now I understand. Yeah. So they have better topological properties. I see. Do you know if actually these are topologically distinct with the distance you defined? We saw the distance you defined. Do you for sure know that they are not homeomorphic?
So what do you mean by saying homeomorphic?
You said you give examples where some of these collections are different, right? Some of them are bigger by giving examples, but you don't give examples why these are not homeomorphic or not with respect to the distance. Do you know if they're completely different topological spaces?
Okay. So I mean, okay. So if we consider these sets, so we have these topological spaces, and we wonder whether they are homomorphic or not, right?
Yeah.
Maybe we can look at the table and see what happens. maybe
I guess
we
some
can
of them are not,
no,
because they have different.
no, it's a very nice question, but
some of them might be still.
No, but I didn't study.
Okay.
To be honest.
Okay. Some of them have different properties. Two of them are complete and some of them are not. We know that. Some of them are not equal, but it's nice.
Okay, any other questions?
Sorry.
Yeah, you can.
Okay.
And also one last thing that I can say, in a bottleneck distance, in a persistence diagram. So you're living here. So this is the birth time and this is for the death time. So when you have two persistence modules, so let's say one is 0, 2, the open interval, and one is half closed. So if you would like to represent these two interval modules in a persistence diagram, you are going to plot the same points. Okay, let's say this is 0, 2, sorry. So even they are not isomorphic, you are going to plot the same points. Maybe, I mean, the interleaving distance, of course, is 0 as well as the bottleneck distance. But in the persistence diagram, you lose some kind of information because these two persistence modules are represented in the same diagram. But when you consider persistence modules and when you consider the interleaving distance, maybe you see the difference between these two persistence modules. Even they are not isomorphic, they are represented in the same diagram.
Before we finish, can I ask one last question? Not this one, related to. You said indecomposables are these intervals. Do you know what are the projective modules on this category of modules over the OSET? Like projective objects in module category sense that.
I guess there is a paper of Bubenik and his student Milicevic. They consider homology theory on persistence modules. I couldn't read, to be honest, but I saw that paper, and they consider some modules and some projective modules. Maybe you can take a look at this one. Bubenik's and Milicevic's paper.
Can you
they consider
over email? It looks like
yes, definitely. Definitely. So
right.
they consider projective. They consider homology theory, homology algebra on persistence modules. I can recommend that paper, and I will email you, Professor.
Thank you. Thanks.
Okay. So any other questions? If not, let's thank Tane again. Okay. Thank you very much.
Thank you.